suppose I need my headphones on.
Yes.
Okay, breakout rooms are being made. Hold on. Okay. Breakout rooms are available.
Right. Assign me and Ivan.
Resistance is futile. And there's Ivan.
Hi, Ivan.
Hello.
All right. Well, I still want to move
We've
this to
lost
the other.
Abby.
Well, she's not in the breakout room yet. This way, Dave can be the moderator in the main Zoom chat. And then once he vets a questioner, he sends them to this breakout room to ask us a question.
But we've lost Abby. Oh, there's John.
There's John. Yeah.
Oh, John.
Ivan, I love your background. Star Trek. A Borg cube.
Resistance is futile.
Did you see the first episode of Discovery this week?
I did not. I did just finish Star Trek Picard.
Okay. Turn it up. Yeah, the first episode of Discovery, I think, was fantastic. One of the best Star Trek episodes.
We're still missing Abby.
Yeah, she must be talking to Dave. They're hatching some dastardly plan. I'm going to go get my water cup because I'm sure I'll get thirsty at some point. And I'll be back. And John, you're on mute, by the way.
Oh, would you bring down that my water glass?
I will.
Thank you.
Okay, now I'm not on mute.
Oh, now you're not on mute. Well, Scott's gone to get water and water.
Ah,
I have about a third of a cup of coffee left, so.
I have water and carbon dioxide.
Excellent.
I have water, carbon dioxide, NOS, and limoncello.
Mm-hmm. In an Erlenmeyer flask. I love it.
Picked it up at Michael's during Halloween a few years ago. I haven't dared to subject it to high temperatures. It will probably break.
Okay, that worked.
Okay, there we are. We're all together. All together now. Scott will be right back.
All righty.
So we're almost moderate.
Well, in the meantime, unless you were in the midst of a conversation, I was just going to say I just came back from walking around in our local national park, which is Minuteman National Park, and I had not realized it, but we had been having some epic weather recently.
Yes.
There are trees down everywhere, and I don't mean little trees. There are, good size, maybe 75-year-old oak trees that have been pulled up by their roots. And some of their roots are the size of my upper arm, so it can't have been easy. In other cases, there were branches taken off trees that, like the branches are as big as a lot of trees. And in other cases, the whole tree was taken down, but not at the roots, but, sort of 20 feet up the trunk, the tree has been decapitated. And again, we're talking, these are New England trees here. They don't mess around. It's just astounding the sheer amount of tree damage that has happened since last week, because I was in the park last week. And I think it's probably the combination of the drought we've been having. And I mean, this is a drought by New England standards, but still, these are New England trees. And probably the trees got weakened by the dryness. And then we did have some pretty significant wind while the leaves are on the trees. Mm-hmm. And then we had a really, really soaking rain yesterday. And of course, when the soil becomes liquid, then the roots can, just go out. But for these various different reasons, I guess, I mean, one,
turn that down. That's really good.
After some major hurricanes is all I can say. It's astounding the amount of tree damage there is there. So, I mean, not that we are lacking in trees here or anything to go around, but it's really interesting the number and the size of the things that have gone down.
And the Scott has returned. Yay!
There's Scott.
Hello.
We won't let everyone else know, but he's barefoot.
Oh, no.
Oh, yes. You know, barefoot in the park?
It's my house. I can be barefoot if I wish.
Well, the dog is barefoot.
That's true.
Or is
No,
he actually
dogfoot.
dogfoot?
Yeah. All right. So I don't know if Mike Albro will be joining us today. I haven't heard from him, but I'll tell Dave to let us know when we start the YouTube stream.
Oh, the dog has a whale.
Okay. Dave's going to start us in 1 minute.
All right.
Abby, did you see some of the emails from this week about the topics related to human evolution?
I didn't take a look at them. I've been kind of busy this week, so I was doing well to make it. So I have not actually seen the emails. I apologize for that, but
Okay.
I'm right now.
Well, I suspect that you'll be able to talk about it given your years of expertise in this area in any regards.
The answer to that will be sometimes yes and sometimes no. It'll depend.
Okay. One of them is that something like 30% of adults now retain an artery in the forearm.
Oh, yeah.
That used to consistently, like 60 years ago, it almost always disappeared after birth, and something like 30% of adults are retaining it. And my question is going to be, is that a sign of genetic drift or is it evolution?
There's
or natural
also the
selection?
thing about a new fratella, a bone in the back of the knee.
Yep.
That's
Oh,
beginning to occur.
Yeah, I heard about the bone in the back of the knee. No
So-
idea about that, but interesting.
We got 10 seconds.
So when you cross your legs, does it start off the circulation completely or what?
It might make it kind of hard to squat.
Yeah.
Yeah. All right, we should be live any second now. I'm going to wait. I'm going to count to 5 in my head, and then I'm going to start our introduction. Hello, everyone. Welcome to another exciting episode of Sidewalk Science. We're live on YouTube, and a reminder that this program is brought to you by the American Humanist Association due to a grant that we've received with our local humanist chapter, which is the Prairie State Humanists. And the Prairie State Humanists are based in the western suburbs of Chicago. We have a meetup site, and most of our meetings these days in the era of the pandemic are broadcast live on Zoom. Feel free to check us out there on meetup.com. Look for Prairie State Humanists. And I encourage everyone to explore the offerings and the philosophy of humanism, especially the American Humanist Association. Now, joining us today are three scientists that are remote. But first, my co-host, Joanne Reed, is a doctor of education and has a background.
And if Dave could put my name up there too.
That would be good. Yes.
Well, I think I can change
Oh,
our name.
All right, we can
to
change
say
our names.
Scott.
This is something that we can do.
I think so. I think we can change our name to
neato.
Scott and Joanne.
Wow.
Let's see.
This
if I
is
can do this.
technology at its finest.
Rename.
Rename.
If you hover your cursor over the upper right, there will be various choices offered to you, and you may have to click on some little thing. Click on the 3 buttons, or else the thing that
Look
says,
at that.
yeah, there you go. There you go.
Technology.
All right. Scott Thompson and Joanne Reed. And then joining us from the East Coast in the Boston area, if I'm not mistaken, is anatomist, biologist, and science communicator extraordinaire and author, Abby Hafer.
Hafer.
Sorry. I knew that, and I've said it correctly before. I don't know why I messed up. I apologize. And then starship designer, actual spacecraft designer, and prize-winning physicist John Doty. Hi, John. Welcome.
I'm laughing at the prize winning part. That was the prize I won. But
Well,
Well, didn't you recently win that NASA contest for
Yeah,
design?
the NASA invention contest. It was a thoroughly daft idea. But NASA now is talking to us about actually implementing. So I don't know. I will see.
We look forward to hearing your further adventures in this then.
Yeah. And then
Do you know any solar physicists who'd like to be a PI? We really, we came up with an engineering idea basically, and we really need a solar physicist to serve as our science contact, because I do black holes and neutron stars and stuff like that. I don't know anything about the sun.
Big ball, sky.
well, this is a good place here on YouTube to give a shout out to any solar physicist that happens to stop by.
Yeah.
You never can tell those solar physicists what they'll get up to.
Well, solar physicists are people like astronomers who don't like staying up late.
As opposed to spacecraft ops people who have no clocks at all. Oh my.
And then also we have joining us today, Dr. Ivan Phillips, who also is a physicist. And Ivan, you can correct me certainly if I'm wrong, but I believe you also have a deep and abiding interest in the philosophy of science. And that's some of your current thinking.
I do have an interest in philosophy, yes.
Great. So without further ado, we have a moderator also that is working. He's the man upstairs, actually.
See, even humans have a man upstairs.
That's right. The man upstairs is David Clark, who happens to be my spouse, and he's acting as our technical guru and moderator today for our chat rooms. And also, if you have questions and you're watching via YouTube, you can enter your questions directly in the YouTube chat feature, and Dave will relay those questions to us via this magical computer that's sitting here. And then also, if you prefer, I believe also on the YouTube stream is information displayed about how you can call into us or join us via your computer. And you can chat with us and join our little hangout room here if you wish. So without further ado, Dave hasn't alerted me about any questions yet, so I thought we'd dive right into some science topics that we've heard about.
Indeed, you were talking about science thing the other day, stars and stuff.
Yeah, so there's a couple of interesting star-related pieces of news. One is that Betelgeuse,
Betelgeuse.
Yeah, not the demon in the movie, but the star, which is a red supergiant star in the constellation Orion. Orion is just now beginning to rise in the eastern horizon shortly after sunset. And it's one of the most photogenic constellations in the night sky. If you've got
The three.
yeah, the belt stars and the Orion Nebula and that thing called the Horsehead Nebula. It's a really, really beautiful constellation. Near the Pleiades, right? And the Crab Nebula and the constellation Taurus. So all kinds
Really
of
cool,
wonderful photogenic things in the winter nighttime sky. But things in the sky are either unfortunately they tend to be either dim or tiny. So to combat both of those technical challenges, our eyes don't do a very good job with either very tiny or very dim. So we typically use telescopes. And one of these days, we have a sister program called Science Sunday. One of these Science Sundays, I think I'm going to give a demonstration of astrophotography using my backyard telescope. So
if you don't know it, he's got a variety of wonderful telescopes. He's got tracking devices so that he can focus in on something and it will follow it across the sky. Cameras, everything else. He's been doing this for 30 years?
about 10 or 12.
Well,
It was one of those hobbies that I decided, I'm not going to wait until I retire. So,
and it's expensive, but he has fun, and that's all that counts. But he's been having some marvelous pictures already. So that's going to be a wonderful program.
Yeah,
Please,
thank you.
please.
So anyway, in any case, the constellation Orion, typically constellations in the night sky are just human
Yeah.
imaginations, right? You know, it's like a connect the dots. You look at the sky and you say, oh, there's a bright star and there's a bright star. And if they were connected by a line, it might make a picture of a bear, or a picture of a swan, or in the case of Orion, the Greeks thought it was a picture of a hunter. And so all of the stars in a constellation are typically not physically related to each other. They're not part of the same star cluster. They don't move through space at the same rate in the same direction necessarily. But visually, we see them close together. And one of the stars that we see in the area of the constellation Orion is one of the brightest stars is Betelgeuse. Beautiful name. I don't actually know where the name comes from. I probably
Is that
read it.
Arabic?
Probably. A lot of star
Yeah,
names
most-
are
a lot
Arabic.
of them are.
Yeah. But Betelgeuse is a red supergiant star, and that's a star that has burned through essentially all of its hydrogen. Hydrogen powers most stars for their vast majority of their lives. And then once a star burns through hydrogen, it says, all right, what's next?
Helium.
Helium, that's right. So it starts burning helium, but it burns helium at a much higher temperature, and the outflowing energy creates more pressure on the outer regions of the star, and the star puffs up like a big hot air balloon. And so Betelgeuse is a really puffed up star that's nearing the end of its life, and it's a red supergiant burning helium. Now, a year or two ago, Betelgeuse dimmed perceptibly.
Dramatically.
Yeah, and scientists were very excited about that. They thought maybe that Betelgeuse was getting ready to do its swan song, its final act, which for a big star like that with a lot of mass would be what's called a supernova, where it runs out of helium fuel, and then for very brief periods of time, brief being anywhere from hundreds of years to thousands of years to a few seconds, depending upon the particular nuclear fuel, it burns quickly through the rest of its available fuel and until it reaches iron. And then once it reaches iron, it cannot generate energy any further by fusing iron, and the star dies. And when it dies, if a massive star dies, it implodes. All the gravity pulls all the material, much of the material of the star back down towards the center, and you get this great sonic boom that shatters the star into space. And we see that as a supernova. Now, I'm not going to go into details about supernova today. We might discuss more of that later. But the interesting point is when Betelgeuse started dimming, they thought maybe it had gone through a transition where it was starting to burn perhaps one of those other non-helium fuels and had only a limited amount of time left before it turned into a supernova. Well, since subsequent to that, they've thought that instead what happened was that there was a cloud of dust and gas. You know, it's a very dirty star. Big giant stars like that emit a lot of atomic debris. So a lot of carbon, nitrogen,
Silicon, all over the place.
Yeah, a lot of detritus comes off of that star, and they think that it was just a debris and dust cloud that wafted in front of Betelgeuse to make it look dimmer from our perspective. And some scientists recently, as was published,
windshield is what you're telling us here.
I'm sorry, say that again.
It was dirt on the windshield is what you're telling us.
Yeah. And so recently, there was an article that some scientists took an even closer look at Betelgeuse. And one of the great things about a star like Betelgeuse is that it's almost like adding a lot of red food coloring to a vigorously boiling pot. If you were to look at the surface of Betelgeuse, you would see a lot of frothing and a lot of convective currents. And it doesn't really have a well-defined surface like a star like our sun would have. It has a sort of a transition zone of just giant plumes of material, and it's really frothy and indistinct. But they looked at Betelgeuse and did some additional analysis of its brightness and its characteristics. And by the way, it's one of the few stars that is close enough that we can actually just barely make out some of the surface features of Betelgeuse. And they looked at it, and the long and the short of this very long-winded explanation is that Betelgeuse is closer than anyone had previously thought. So not close enough to fry us once
Which is good.
once it turns
Which
into a
is
supernova.
really good.
That's right. But part of the other part of this study shows that, or at least claims that Betelgeuse is still burning helium. So it still has at least 100,000 total years left of life.
Darn. And I was hoping for a big show.
Yeah. So I'm looking up now to see what the distance is. So Betelgeuse 25% closer than scientists previously thought, and that's quite a change in its distance. So they think it's about 530 light years from Earth, rather than 750 or so, which was the original estimate.
And that's not close. I'm sorry. That's a far, far distant thing.
Right. You know, speaking about the distance of the stars, I heard Neil deGrasse Tyson once use an analogy that I really love. He said, if our sun were the size of a period on a printed page, then the closest star to our sun would be 4 miles away. That's the closest star. So
And
stars tend to be pretty widely
that's what,
distributed.
4 light years?
Yeah. About
And when I put on my gamma ray burst astronomer hat on, I'm studying things that are 1 billion times farther away than that closest.
1 billion.
billion.
10 to the 9th. Wow.
Yeah.
How do you know, John? How do you know that things are that far away?
For gamma ray bursts, the main way we know is we look in the optical and the infrared, and we see the light that comes out after the gamma rays. And that light travels through whatever matter is in the way. And we see absorption lines due to the host galaxy of the star that blew up and made the gamma ray burst. As well as often we see additional lines at lower redshift for things that are between here and there. And then we have this famous calibration between redshift and distance from the supernova results. And that's how we know how far away they were.
Wow, that's amazing. So you can't tell just by looking at it with your eye. I mean, you can't even see these gamma ray bursts without a special telescope, right?
Yeah, and the crazy thing is that the properties of the bursts are such that it's really very difficult to tell from the gamma rays whether you're seeing a burst that's nearby or far away. The far away, because what we see in a gamma ray burst is beamed radiation, and we're often not in the center of the beam. We tend, because there are many fewer of them nearby, we tend to see the nearby ones way off the center of the beam, and they look relatively faint, and they look what we call soft, which means the gamma rays are not of very high energy. When we look farther away, we have a higher probability, because there's so many of them farther away, of catching them in the center of the beam. And then we see them and they're brighter and harder. And the curious thing is that the relationship between the beaming and how the light both red shifts and fades out with distance is about the same.
Huh.
And so this is a weird coincidence. And so it's very difficult to tell, looking at the gamma ray burst, whether it's a half a gigaparsec or 5 gigaparsecs away. These are all extremely large distances, but nevertheless, it's hard to that's our problem.
Hard to narrow it down.
Yes.
I have another question about gamma ray telescopes and whatnot. Well, 2 questions, really. I hope you'll allow me 2. One is, do we detect these from Earth, or how do we, or do we have to detect them from above Earth's atmosphere? That's the first question. And then the second question is, can you do spectroscopy, picking apart the individual frequencies within a band of gamma rays to get more information?
The answer is, first of all, that we do almost all this from orbit. Most of it's done from Earth orbit. There was for a while something called the Interplanetary Network that involved gamma ray detectors on interplanetary spacecraft that localized gamma ray bursts by looking at the difference in the time delay of the burst at different places in the solar system.
Mhm.
That no longer is functioning, and our ability to find them now depends more on assets in low Earth orbit, particularly the Fermi Observatory gets sort of crude positions for them. And if they're lucky, the Swift Observatory gets very good positions using coded aperture camera. But then the next question was spectroscopy. And the answer is that we do spectroscopy on them. And what we see is not a very exciting spectrum. What they have is they have a spectrum that, in the units I like to use, it ascends to a very broad peak in the X-ray or gamma ray band as you move up in frequency, and then it declines from that peak. But the slopes are very shallow, and so if you plot it in what we call power units, sometimes the spectrum looks like this, and you don't see any lines or anything like that. It's very it's very featureless.
Okay, it's not nearly as instructive as visible light spectrums then.
Yeah, the visible light is actually pretty much an extrapolation of the low energy gamma rays. But the thing that happens with the visible light is that gas, interstellar and intergalactic gas, absorbs visible light at specific wavelengths. And so at visible light, what you see absorption features superimposed on this boring, featureless continuum. And the absorption features are the things that we use to get the distance.
Fantastic. That's amazing.
And that's where atomic absorption spectroscopy had its birth.
Yes, Fraunhofer.
Yes, good old Fraunhofer. The good old Fraunhofer lines, and until we were looking at emission lines, but then we said, well, wait a minute, if the sun can do it, why can't we? So we built bulbs with a specific element in it, and we shine it through a flame, which is aspirating a particular solution, and we look at how much light is absorbed, and that is a direct measure of the concentration. And we've been using that for about 50 years now. So it's a relatively new technique, but then again, 50 years in this world, that's old fart stuff, right?
Yeah. Wasn't there some German, if I remember correctly, boy, I wasn't planning on discussing this today, but it brings to mind something I read about some German scientist who spent much of his professional career compiling essentially an encyclopedia of spectroscopic lines that was published around the turn of the century.
Well, Fraunhofer was the first one. I don't know of anyone else, but he was instrumental. And of course, everyone said, no, it can't be, because again, the sun is pure. There's no imperfections in it. And he kept going, but there's a line there.
Yeah, I think there was a female astronomer who was also instrumental, so to speak,
very likely,
in discovering elements on the sun before they were discovered on Earth. Mm-hmm. And I apologize sincerely, I don't remember her name right now. I bet Mike Albro would know if he were here with us today. Speaking of corrections, things that I might get wrong, I was wrong the other day when I said that black holes have magnetic fields. I did a little bit of research on that. Black holes are almost like superconductors. They expel magnetic fields. But most of the black holes that we detect, obviously black holes don't emit any radiation of any sort. So we can't detect them by using any kind of telescope. But the black holes that we know about because they're eating other material. And when they're in the process of swallowing matter into oblivion, as it were, that matter gets compressed as it squishes into a black hole.
That's a technical term.
Squishes, yeah.
Squishes. Mhm.
And heats up, and that hot matter becomes a plasma, and that plasma, typically it's in the form of a kind of a donut or a disc, and that plasma, just like the plasma inside a star, or analogous to the plasma inside a star, can generate its own magnetic fields. So John, I hope John and Ivan, I hope I got that right.
Yes, you get dynamo processes similar to what makes the Earth's magnetic field, and from a spinning conductor. Now, the Earth doesn't spin that fast. When you have a black hole, the plasma is circulating around it at relativistic speed, at a substantial fraction of the speed of light. And about 20 years ago, theorist Roger Blandford came to MIT and gave a wonderful talk on dynamo processes and we're getting back to gamma ray bursts, on dynamo processes in the accretion disks that we think are down inside the exploding hypernovae that make gamma ray bursts. Because we think that what's going on is that you get a core collapse of a supermassive star, and then that core collapse produces an accretion disk that's down inside the star, and that makes a dynamo that makes an enormous amount, functions as an enormous electric generator and drives the formation of these jets that make these beams of gamma rays.
You say that happens inside a star?
Yes, it happens inside the star.
Wow.
And probably if this idea is right, then sometimes the jets don't make it out through the outer layers of the star. They're frustrated by all this mass in the way. And when that happens, they wind up depositing their energy in those outer layers and blow those outer layers off. And we see an ordinary supernova, an ordinary type 2 supernova. But if the jet manages to blow its way all the way through the outer layers of the star, then and emerge into the space around it, then these old stars blow off shells of gas. You were talking about Betelgeuse burbling and all that. These old stars blow off shells of gas as they're dying. And what seems to happen is that the jet of electrons and positrons and electromagnetic radiation comes out through the star, and it runs into the shells of matter around the star. And when it does that, it makes shock waves, and the shock waves convert the electromagnetic energy of the jet into gamma rays, and that's the gamma rays we see. That's the fireball hypernova model of gamma ray bursts. But the interesting thing about this talk, which was fun, was that Roger, because he was analyzing what goes on as electrical engineering, he was doing everything in practical units, volts and amps, and not the crazy units that we use in theoretical physics. Okay, and the physicists in the audience, the theorists in the audience, were just scratching their heads. What are these numbers and what do they mean? And afterward, I found myself in great demand because I'm a switch hitter and I can work in either set of units.
So they were having, teravolts or petavolts or those.
Yotta volts.
Yotta.
Have you ever heard the SI prefix yotta actually used? Zeta amps.
Wow. Big.
So John, how long do these gamma ray bursts last?
I'm talking about what are called the long soft ones, which are still pretty hard, but they're typically a few seconds to a few tens of seconds for the long soft ones. There are shorter ones which we think come from a different mechanism. And in fact, we've seen one example where we're quite sure that it came from that mechanism. And that is that we think that they are mergers of neutron stars with either black holes or other neutron stars.
And that's what creates gravity waves too. Right?
We've seen one of those in gravity waves and as a gamma ray burst
Wow.
at the same time.
Yeah.
So yeah, that's a different class. And then there's a third class of gamma ray bursts, which we call soft gamma repeaters, which are even softer, and they are in absolute terms much fainter, but they occur from neutron stars in our galaxy, so they're enormously closer. And so we see them.
Wow. We've got an astronomy astrophysics kind of question from a YouTube viewer. Let's see. Marinelle wants to know, Peter. Peter wants to know, how does local gravitational activity in distant galaxies, especially those being absorbed by other galaxies or black holes, so maybe galaxies are being cannibalized or merged, to use my own language, how does local gravitational activity in those sorts of galaxies affect the so-called uniform expansion of matter in the known universe? And I think I could take a shot of that, but Ivan, do you want, I'll give you dibs on that answer if you'd like.
I would think that it doesn't affect it very much, but it's not my area of expertise.
We need Mike Albro here.
Well, in my book, I did a little bit of research about this. Speaking of the devil,
Oh,
Mike Albro.
Angels. Am I an angel or a devil? I'm in between. Anyway, hi.
Oh, you're an angel to us. I've got a question for you in just a moment, but first I'm addressing a question from a YouTube viewer. How does the local gravity of interacting galaxies or interacting, for example, mega black holes, gigantic black holes, how does that comport with the notion of an expanding universe? And in my book, I write a little bit about this. I talk about local effects can significantly overcome the tendency of empty space to expand, to increase in volume. So the effects of what are called dark energy are so feeble that the matter, the electrostatic forces that hold an asteroid together, typically it's not even chemical bonds, it's just electrostatic bonds or maybe gravitation if an asteroid is big enough. Those feeble forces are plenty strong to overcome the expansion tendency of space. So it doesn't take much gravity at all, and certainly trivial amounts of electrostatic or electromagnetic forces to overcome this very feeble tendency of the universe to continue expanding. So on local scales, things can collapse and form new stars. On local scales, galaxies can interact with each other and move more closely together.
In fact, we're going to collide with Andromeda.
That's right, the great Andromeda galaxy. We're going to be colliding with that. I don't know, probably after this program.
Oh, yes.
A few billion years after the program.
Scott,
What's 3 billion years between friends?
I have a question about this to you because I don't quite understand it, honestly. And as a physicist, I don't understand it because let's say the dark energy is expanding the volume of the universe, and it's gone by a factor of 2 in the last 1 or 2 billion years or whatever. So if that is a property of space, why doesn't it apply to the space within us, within our matter, within our stars, within us too? And yet atoms seem to be the same size. They haven't changed in size, but the whole universe has. So if there's a property of space, I don't understand really. I mean, I understand that gravity is dominant, but
I think that's it though, right, Michael? Is that it does affect space everywhere, but it's this extra term treated like an extra term in Einstein's field equations. And because it's relatively small, it's just not going to have very much effect over short distances.
compared to normal gravity.
I still don't quite get it, because if it's a property of space and space is doubling in size every hundreds of millions of years, doesn't that apply to space within atoms as well? Even though it's much smaller than the electromagnetic force, of course, but I don't really understand it, honestly.
I think it's called the metric of space-time in general relativity. It's the geometric description of the scale of space-time in different regimes. So in regimes where there's a lot of matter and in regimes where there's not much matter at all. And matter embedded in space-time essentially binds that space-time more strongly than dark energy tries to spread it out. So
well, that's not real. I wouldn't say that so much. The idea that what are you using as a ruler? Space, the dark energy expands space-time, but if you're going to talk about how much it expands it, you have to figure out what you're using as a ruler. And the answer is that what we use as a ruler is atoms. And so what's happening is that the dark energy is expanding space relative to atoms. If it wasn't expanding space relative to atoms, we wouldn't talk about expanding space, because we wouldn't have anything to refer the expansion of space to.
the atoms themselves, our rulers would get this big just by the same factor.
Right. And so if the space expands by twice, but the ruler you use to measure it expands by twice,
You don't see it.
Nothing changes.
what happened? Nothing. So the whole concept of saying that space is doubling in size requires you to refer back to a ruler. And what we use for rulers, well, right these days, what we use for a ruler is we use a cesium clock and the speed of light. And we just, the definition of the meter is based on how fast a cesium clock ticks and then how far light goes in that time.
But John, the wavelength of light, the wavelength of electromagnetic radiation is increasing with the size of the universe, right? That's how we see it.
You can think of it, yes, that the cosmic microwave background is getting stretched out by the expansion of the universe. That's one way of seeing it. But actually, in our normal way of thinking of it as astronomers, we just think of it as Doppler shift. As if you have an expanding universe, the stuff farther away is moving away from you. And so what you see is the wavelength stretched out. You see the frequency reduced.
I used to think that, yeah, it's simply the redshift, Hubble's redshift and so on, is simply a Doppler shift of things moving away, as the usual Doppler shift is. But then I was told by professionals that actually the wavelengths, as the universe expands, the wavelengths of light expand too.
Yeah, so Sean Carroll, who's a fairly active general relativist, has written about this. I read his blog entry a couple years ago, and he said that it's technically misleading to think about the wavelength of light expanding. So when you think about the surface of last scattering, which is what generated the cosmic microwave background photons that we see, that's when the Big Bang was hot, and it cooled off to the point and became, prosaically, I'll just say, the density fell enough that photons could finally escape from the hot Big Bang. And that's what we see as the cosmic microwave background. What Sean Carroll has written, if I'm remembering correctly, is that you got to be really, really careful when dealing with general relativity. One of the conclusions that the sort of naive view that the photons stretch out as space expands, that naive view leads to a violation of the conservation of energy, because a infrared or a microwave photon has less energy than a a bright red photon, which is sort of how this all started back in the day. The cosmic microwave background radiation started as red. In any case, if you get a violation of the conservation of energy just because something is moving through space, is it losing energy to the stretching of space? That's one of the ways that some authors have written about it, and that is, according to Sean Carroll, also misleading. So what Sean wrote was that we are in a very, very different frame of reference today compared to the frame of reference, the relativistic frame of reference, during which the cosmic microwave background was emitted. And it's the change in reference frame related to the geometric properties of space-time today compared to the geometric properties of space-time 13 billion years ago, that when we compare reference frames, we see different measurements of the same phenomena. So it is a purely relativistic effect. It's not because the photons lose energy or get stretched as they travel. It's because we're looking at something, a signal sent to us from a vastly different relativistic reference frame.
Well, I'm not quite sure I buy this energy non-conservation argument, because I see that the wavelength of the photons, as if they're stretched, the wavelength gets longer and they have less energy, but there's more space. So the total energy is constant, even if the energy density goes down. Right?
Yeah, the energy per photon, though. So where does a given photon's energy go if it decreases just because it's moving through space? It's not absorbed by anything, right? It's not absorbed and re-emitted.
As a particle, but as a wave. In this case, it's a wave, and as you stretch space, the wavelength increases and the length of the wave increases as well. So the total energy of the wave is constant. The photon is only realized when it interacts with something and becomes quantum. Otherwise, it's a wave. I mean, you shouldn't think of these photons in the space as being particles flying around. They're waves on this scale. So it's obviously a very interesting, very complex thing, and I still don't fully understand that.
I'm extremely simplistic in this. I look at the core of the atom, the nucleus, and it's held together by incredibly strong forces. And then you look at the forces which are expanding the universe, and they're incredibly weak.
Right.
So it's going to take a hell of a long time before that extremely weak energy is sufficient to just tear this incredibly tight.
And you're onto something there. So one of the things that theoretical physicists have hypothesized about is something called the Big Rip.
Yes.
That very, very far in the future, Yahoo years, something like Yahoo years, to use John's numeric term again, dark energy, the density of dark energy will be sufficient to overcome the electromagnetic and even the strong force binding nucleons within atoms, and all composite particles, including nuclei within the universe, will shatter. But that's very
yeah.
But will that also destroy protons? Which again,
the protons will all have decayed, right? In terms of 40 years, a lot have decayed, right? But anyway, I come back to my point. It seems that galaxies themselves are not expanding.
Right.
That's right.
But the universe as a whole is expanding.
That's right.
So if that's due to space expanding with respect to anything you like, a wavelength of a photon or the size of an atom, why does a galaxy not take part in that, and why do atoms not take part? I don't quite get it. It doesn't answer me to say, oh, it's insignificant, because the universe is actually doubling in size every few hundred million years. So why?
Well, back to Ivan's point, the cosmological constant factor in the model, the theoretical model that we use to describe gravity mathematically, are called Einstein's field equations, and there's something like 16 of them. And within those equations is a factor. It's represented by the Greek letter lambda. I don't know why they chose lambda.
It was hanging around. It wasn't doing anything at the time, and they said, "Why not?"
Why not? Right.
Okay.
So you might hear about the lambda CDM model of the cosmos. Lambda is the dark energy factor, and CDM is cold dark matter. So that's the theory of the cosmos that involves other things besides just prosaic gravity.
So yeah, think of this term as adding some, the dark energy is adding some, affecting the curvature. It's some weak factor. Well, the curvature near galaxies is dominated by gravity.
Right.
Dominated by, I agree, dominated by. And the distance between two galaxies is not dominated by gravity. It becomes dominated by dark energy, which is pushing them apart, right? If they're not.
Oh, it isn't,
Not if
because
they're nearby each other.
No, okay. But
because here's the deal. You're thinking of dark energy as a separate thing that's pushing them apart, but their own gravity is pulling them together, and the scale of the distance between two galaxies is controlled by both their effect, the effect of their stress energy on the geometry, as well as the effect of the dark matter on the geometry. But between two galaxies, the effect of the dark matter on the geometry is small compared to the effect of their own stress energy. And so their own stress energy dominates, and
John, you said the effect of the dark matter is
dark energy. Sorry, dark energy.
Yeah, right.
Yes.
Dominates, but if you accept that dark energy is a property of space, of the vacuum, that is causing the universe to expand faster and faster and increasing its size, why does it increase only the size on a large scale and not also on a smaller scale? It's a scale invariant thing. It doesn't depend on the scale of things.
It specifies the metric or the relative scale of measure between two different parcels of space-time. And that metric involves a term that's due to gravity and also a term that's due to dark energy. And when the gravity term is really big, it dominates the metric specification, the size specification of distances in that region of space where there's enough matter to make gravity by far the overriding.
It's an enormous difference.
But you're saying, I mean,
billion of this and one of that.
Dark energy does expand atoms, but it's just such a small effect that we haven't been able to see it. Are you saying that or not?
And in the far distant future, when dark energy becomes greater, and this is a part I'm not clear on, because my understanding is dark energy, the density remains constant. But I think the accelerating universe implies that the amount of dark energy per unit volume may actually be increasing. I'm not sure.
There are different dynamical theories of dark energy, and nobody knows. And you got to do the measure.
You want to hear my theory about dark energy? Do you want to hear it?
Sure.
Okay. If you suppose that dark energy is like a field, like the Higgs field, for example, but it's a field in the vacuum that is uniform, it's got no direction, but it's a field. Now, in quantum field theory, all fields have quanta. So photons and electromagnetic quanta. And so the dark energy field should have a quantum that goes with it. Then you can ask, well, if that's true, what are the properties of that quantum? And obviously, it's totally neutral against all the forces and so on we know, except gravity. But it's a repulsive gravity. So now imagine that you have a repulsive gravity between two of these quanta. Now, Newton said the force between two particles is the product of their masses, okay, and it's attractive. But if the product of the masses happens to be negative, it's repulsive. So the product of two things that's negative is an imaginary number, right? So if these quanta have their mass is actually not real, but it's imaginary in the sense of the square being -1, then these could be candidates for the quanta of dark energy. Now, the thing with imaginary mass is something called a tachyon, right? It always travels faster than the speed of light, because as you know, the equation is E squared is P squared plus M squared. And if the mass is negative, if the mass squared is negative, then E is actually less than P, which means
energy and momentum. P is momentum.
So energy and momentum. Normally, particles have E squared is MC squared plus P squared C plus 4. But anyway, forget the C's for the moment. So normal massive particles with a positive mass squared, normal particles, positive mass squared, E is greater than P, and the speed is the momentum divided by the energy, which is always less than 1 for a normal particle with positive mass squared. But if the mass squared is negative, as it is for a tachyon, then E is less than P, and the speed is greater than the speed of light. So people say, oh, you can't have particles with a speed greater than the speed of light. And I say, well, you can actually. They're not forbidden by relativity. Relativity just says you can't have any particle with a real mass that travels faster than the speed of light.
It accelerates to a speed equal to or greater than the speed of light. It's even,
Okay,
it's
so
even a little more.
right. So these tachyons, if they exist, and I'm not saying they do, but they have been hypothesized since I got my PhD in started it in 64. Then they always travel faster than the speed of light. They never come down below the speed of light.
And it's hard to slow them down
Well,
to the speed of light. The equations sort of act backwards.
they would have, so it's backwards. So a tachyon with zero energy would have infinite speed. Okay,
Right.
That means it's right across the whole universe in no time at all. But we know zero energy is not possible because Heisenberg says you can't have absolute zero energy in a finite time. Okay, so but give it a very small energy and it slows down. You give it more and more energy if you knew how to do that, and it slows down and comes down towards the speed of light from above. Unlike normal particles, which can get up to the speed of light from below, but never quite reach it, okay? So this is the idea that you have a gas of tachyons, now, that is a quantum of dark energy. Now, we know that tachyons cannot have normal interactions with particles like electromagnetic or strong or weak force because we've already detected them. We haven't. So they obviously don't have any of those forces, but can still have purely gravitational force. Now, and then you can say, well, what else can you say about them? The mass has to be extremely low. The mass is imaginary, so called I gamma, where gamma is a real number, gamma, big capital gamma, for some reason. And this means that really they're not easily, you can't detect an individual tachyon. I don't know how you can do that. That's a problem with this because how can you detect an individual graviton? You can't. Tachyon any more than you can detect an individual standard graviton. They're just so weakly interacting. Still, it has consequences. You can work out the equation of state of the universe. It has 75% of its energy in these tachyons. I've actually put on the internet. There's a paper I wrote about this, and if you search for author Albro and title tachyon or dark energy, you'll find it. I mean, it hasn't received attention, but I gave a talk about it, and it's not been poured total cold water on, except people say, well, we can never detect
Can't
these.
measure it. Yeah.
Of course, it's tachyon.
Do you?
Still, that's my theory, and I'm sticking to it. Okay.
All right.
Michael, do you recall why the mass is constrained to be very small?
Yeah. So let me think. It's coupling to normal matter being only gravitational. How actually, I had to think about the answer to that. There is, when it operates on the scale of the universe, it has extraordinarily long wavelengths in the parsec, megaparsecs, and so on. But that means very small energy,
Which is small mass or small imaginary.
Small imaginary mass in this case. And actually, if you search for you Google tachyon dark energy, you will find various papers about that. But I haven't seen anyone that specifically is saying, look, these are maybe the quanta of the dark energy field.
So we've talked about a couple of points that for our viewers, I think we'll take at least a minute to clarify, and then I want to move on to some topics in biology, evolution, and anatomy. But I want to clarify this notion of imaginary. And when a physicist or a mathematician talks about an imaginary quantity, he's not talking about she's not talking about the Harry Potter universe or some kind of purely fictional construct. When a mathematician or a physicist talks about imaginary, they're talking about an unfortunate name assigned to a mathematically viable, useful, and highly relevant kind of number. It's a whole new kind of number. And it is necessitated at the very least by solutions to the equation of a sort the square root of -2 equals x. And to find x, you invoke what are called imaginary numbers. And some of you may have heard about that in high school math or in college math. I believe that the name imaginary is really unfortunate because they have very real consequences in things like electrical engineering and quantum mechanics.
Yeah, let me add something to that, because unstable particles, they don't have a really absolutely pure mass. They have an imaginary component to their mass, which is interesting because in quantum mechanics, if you have something with a sine wave, the wave function of a particle with absolutely precise momentum is an infinite sine wave. All right, it's an infinite sine wave. Now, if the particle decays, its wave function has to decay, dampen down, which means that it's mathematically, it's if you put in a wave equation, the energy or the mass has got an imaginary component, which is responsible for the damping. A really unstable particle has got quite a large imaginary component in its mass.
For the damping factor, because it's unstable.
The damping factor, right.
Right.
But particles with no real mass, purely imaginary. Actually, I have a little story, if you don't mind, about this. It's a bit. I happened to be at CERN, and I happened to be in the cafeteria one evening. That day, Stephen Hawking was at CERN, and he was giving a talk in the auditorium. And of course, it was chock-a-block. I mean, absolutely full hours ahead of time, so couldn't get in or anything like that. But I was sitting outside the cafeteria that evening, and out comes Stephen Hawking, surrounded by his retinue, his nurses and so on, and his students and everything like that. And they were looking for a place to plug in his computer. So Carpe Diem, seize the day, I went and helped. And I sat down and I actually asked Stephen Hawking about, because he's sitting there totally immobile, whether dark energy could have something to do with tachyons. And one of his, of course, he didn't respond at all, but one of his smart young physicists in his entourage said, yeah, we know that tachyons would make the vacuum unstable. So you can't have a vacuum instability. My response was, well, if the universe is actually blowing itself apart, that looks like an instability of the vacuum to me. I don't think he meant it quite like that. But anyway, that was my response. I never did get Hawking to wake up, but he was thinking.
What a great story.
Yeah.
All right, I'd like to move on now to some questions of biology and evolution. We've got about half an hour left. And the first topic I'd like to bring up is a couple stories we've seen recently about ongoing human evolution.
Yeah.
We'll start with a story about an artery in the forearm. And this artery is common in embryos and human embryos as we develop. And then shortly before or shortly after birth,
I don't remember which. But
yeah, this artery essentially deteriorates and vanishes from our arm. And something like 60 years ago or so, it was very rare for an adult human being to maintain this artery beyond infancy. Now, a study done, I believe, in Europe has shown that something like 30% of adults that were surveyed retain this additional artery in the forearm. And this has been put forward as a sign of human continued evolution. And I thought, Abby, this would be a great opportunity. The question that immediately came to my mind about this was, and I don't have a presumed answer to this, so I'm just throwing this out there, is do you think this could be better explained? Obviously, it's real. People have measured it. Could be better explained by a selective advantage. That's one way that evolution happens. Sexual selection. That's a second way. Well, I love that artery in your arm. Or the third way is something called genetic drift, which is just a trait becoming more prevalent in a population because of essentially random amplification. So, Abby, you want to take a shot at that?
Well, yeah, I'm going to start off with your basics here. And the basics here go back well over 40 years because I can remember learning it in college when I was taking anatomy. And my professor then said that when it comes to anomalies, you're likely to find a fair number of anomalies in the circulatory system, if any place, because to a large degree, it's a matter of functionality. So long as the blood gets where it's going, exactly where the tube is or exactly how many of them there are is kind of inconsequential. So as a result, if you're basically, you'll find a lot of sort of, variation and small things that are different between individuals in a population in the circulatory system, because as I said, exactly where the tubes are and exactly how the blood gets where it's going is inconsequential so long as the blood gets there.
So natural selection doesn't operate on that.
I mean, if you have a major arterial problem, natural selection will definitely operate on that.
Yes.
But as I said, just in terms of the layout of all of the tubes, exactly where the smaller arteries and veins are placed, or whether there's 2 of them or 3, or whether it goes here or here, it's not that important to your survival.
Right.
And so you will just see lots of variation because those variations are not sort of harshly winnowed away by natural selection because it doesn't really matter that much. So it's kind of the deep background answer is what I just gave you.
The article progressed on several other lines. It says things like, as the human face changes over time, we're losing the third molar, the so-called wisdom teeth, because our face is shortening. Also that our long bones, especially in our legs, are increasing in length relative to the rest of us. And that amongst other things, we're growing a fratella, that is a patella in the back of the leg, in addition to the patella in the front of the leg.
kneecap, right?
So instead of a kneecap, we're developing a back of the leg cap.
Huh.
And they're pointing out all these things that are just sort of occurring and going, is this evolution?
Well, thinking of the shortening of the face, there was a recent study that came out, and I would have to go back and dig it up. But basically, the conclusion was that this is because of changes in diet, that the length of the jawbone is influenced by how hard you chew as a child. And so since we have softer diets and we're cooking our food and we're cutting it up more than people did in the past and grinding grain into bread and all this stuff, our jaws have shortened because we're not exercising them, and that causes the bone not to grow quite as much.
Well, that brings into mind
that's not evolution, that's a lifestyle change. And presumably if we went back to having tougher diets, our jaws would get longer. Now, as for this arterial thing, it's happening way too fast for evolution. So I think it's got to be some lifestyle thing.
Well, that brings up 2 things. Abby, you can certainly correct me if I'm making an error here. But one point is that evolution does try to favor things that use less material and less energy, as long as it doesn't impose a survival penalty. So if it takes more energy and more material to build a bigger, stronger jaw, and that's no longer needed for survival, that will be selected out without you having to die because you have a large jaw necessarily.
Well, but you kind of do have to die because you have a large jaw, because that's how it works. But the study involved studying people with similar genetics but different diets.
Mm-hmm.
Right.
And
what John is getting at here is an interesting thing having to do not even with genetic expression, but essentially with development and postnatal development, I will say. Having to do with what you do with your body will actually influence how you look. And that can include even things like whether if you chew a lot. Okay, now I will back up a little bit again because one of another thing that you learn in anatomy which is really cool that we didn't understand until maybe 20 years ago, is that bones change in adulthood. This was something we didn't fully realize. So that you've probably heard of osteoporosis and things like this. But the point is that, okay, what will affect both bone density, but also bone size, like the girth of a bone and things like this, not the length of a long bone, how tall you get. It's very difficult to change the length of your bones as an adult, but it is relatively easy to change the girth of your bones as an adult and the density of your bones as an adult, which is something we didn't know until about 20 years ago. But
archaeologists use that, or anthropologists and archaeologists use that to determine if bones of people in Pompeii, for example, or Herculaneum were laborers or not.
Right.
Right. A farmer will have big, heavy bones, whereas a person who's working at a computer all their lives will not.
Right. And that comes down to both diet, the amount of calcium in your diet, and the amount of vitamin D that you're getting either dietarily or through the sun. But also from the amount of what is called weight-bearing exercise that you do. And weight-bearing exercise is what it sounds like. It's sort of maintaining your body against gravity, but anytime essentially that your bones are being stressed. So yeah, a laborer that's busy hitting things all day or picking things up and so on, such that you are stressing your bones. It's really cool. What happens is that when your bones are, pounded in some way, if you, jump and land, when your bones are stressed in that way, the crystals in the bones, the calcium crystals basically emit a very, very weak electric signal.
Is it a scream like, ouch?
Yeah, more or less, except they do it electrically. That actually attracts bone-forming cells to that area, so that more bone grows where bone is being stressed. And that is strictly a physiological response. It's not, evolutionary. I'm going to wait till this plane goes overhead. Well, John knows about this.
Yes. Well, I actually was aware of it and employed it this past year because I broke my ankle. And as soon as I got out of the cast, I was walking 3 to 5 miles a day.
Yes.
And lo and behold, my rehab took 6 months less than it was supposed to.
Right. Wow. Yeah. When it comes, the tricky thing with things like that is that essentially what is good, you have to stress things the right amount. Too much stress and you can re-break things, or if it's a joint injury, cause yourself problems. But on the other hand, sort of the right amount of stress, which can actually be quite a bit, will actually make your bones both more dense, but also that you can increase their girth. So as I said, it's calcium, it's vitamin D, and it's weight-bearing exercise. And so getting back to the jaw, this can apply to jaws as well. If you're busy doing a lot of fairly heavy chewing and stressing those bones a bit, you're going to be attracting bone-forming cells to that area, and you're going to wind up with a more massive jaw. And that doesn't have to do with evolution. That has to do with kind of this fun, it's sort of, well, I mean, I've told you what it is, but in terms of evolution, it's essentially a little bit of, I won't call it choice because it's not, I'll just call it variability based on your life. Evolution has given you a range of options is kind of what it comes down to. And if you use the option of having to chew a whole lot, then you wind up getting a larger jaw. If you don't chew a lot, then you don't.
Well, the same thing happens with brains, right? Brains are one of the most plastic tissues in the human body. And this old adage, use it or lose it. There have been studies that show that people that have early onset dementia, if they become more active with solving puzzles and doing intellectually challenging things, they can statistically delay well, to a statistical significance, delay the onset of some of the more severe symptoms. I'm not saying this is a cure, but one of the pieces of evidence that using your brain changes your brain.
And we're also going to take right here that
These
they
changes,
talk about the old dog that can't teach new tricks. Well, as the dog continues to learn new tricks through life, then even as it ages, it's going to be able to do new tricks. It's when you ossify that it goes away.
right, but presumably it only has anything to do with evolution if any of these changes actually affect the DNA in the sperm or egg of the parent of the next generation, right? Otherwise they don't. Okay, is that correct?
Right.
That's correct. Well, there are two ways to look at it. One is that if you exercise your legs and you make your bones thicker, that's not going to affect how thick the bones of your offspring are.
Right.
But the other way to look at it is that evolution in the long haul is going to favor the survival of organisms that adapt to the stresses in their environment. And so you are pre-programmed to make stronger bones if you have higher stress on them by evolution.
Essentially, if your DNA gives you a range of options, like a range of options with jaw size and this kind of thing, that's advantageous. As for brains obviously are interesting in lots of ways. Brains are energy hogs.
Yes.
So even though we as a species like to think that we are very smart, and that's one of the things that we pride ourselves on, so we think that all organisms really, ought to want evolutionarily to be as smart as possible. Not actually true, because brains are energetically very expensive. So if you can get along with less, you may last longer in a starvation situation. We as a species have kind of, put a lot of our poker chips on being smart. So, we tend to have large, energetically expensive brains. But interestingly, again, until maybe 20 years ago or so, we thought that you did not get any new brain cells beyond a certain rather young age. That neural tissue was simply set at zero reproduction. So once you reached a certain number of brain cells, you had to take care of them because you weren't getting any new ones. And that is still true. We still know that to be sort of true, I guess is the way to put it. This is why, for instance, spinal cord injuries are so hard to heal, because you don't have a lot of reproduction. If you break your bone, as John said, the bone will heal. Spinal cord injuries don't. So there was a lot of evidence that neural tissue does not reproduce the way that other tissues reproduce. But there, it's biology, so there's always a but in there.
Yeah, like salamanders that can grow a limb.
So, Abby, you said, the brain uses a lot of energy, and I know this is true, but do you understand exactly what is it that's using the energy, and what's the budget? How is the energy being used in the brain? What is it that's using so much energy in the brain?
Okay, that I am less sure of. I can tell you that they are energy hogs. We know why muscles use energy, because they're busy doing all of this movement. I couldn't tell you exactly what the brain is using the energy for. That's a really interesting question, and not one I've looked into. So I wish I could help you, but I can't.
So
Pumping ions back into cells after axon discharges.
right.
Pumping ions back into cells after the axon discharges.
Well, yeah, if you think it's all just a matter of active transport, okay, that sounds pretty good to me.
Because the brain cells are very busy in terms of releasing and then recovering ions, as well as synthesizing neurotransmitters and all that. They're very busy cells, and I think that's
pumping ions that is using electromagnetic energy to push them. This implies that when you're sleeping or not active, the brain is using a lot less energy, right? So Can we
Depends on
monitor
the phase of
Oh,
sleep.
but the fact is that the brain, even when you're sleeping, is cycling.
Very active.
The machinery is still running. You're not consciously thinking, but the machinery is still going through the motions, and you get brain waves.
Right. It's somewhat less active. It's still doing its thing, as John said. And interestingly, that's what makes REM sleep so interesting, is that when the brain is in REM sleep, it looks like it's awake.
It turns on. Yeah.
In a
So
sense,
I've never seen a graph of minute by minute or second by second the energy usage of the brain.
uh-huh.
Can we measure that? I mean, of course, we can measure it. But I've never seen such a graph to see. how it varies.
fMRIs can do that, Mike. So functional magnetic resonance looks at oxygen consumption levels in living tissue, and using functional magnetic imaging, they have looked at sleeping brains and waking brains and whatnot. And Abby is absolutely spot on from what I've read, is that during the period of REM sleep, the sleeping brain during dreaming is almost indistinguishable in its energy usage from a waking brain. But there are periods of time during deep sleep when brain activity diminishes fairly significantly.
Right. And then there's one hypothesis around REM sleep, that it evolved basically to warm up the brain from time to time. But the other cool thing about fMRIs is that not only you don't just see that the brain is using energy, you see which parts of the brain are using energy at any given time. So that with different stimuli or different activities or this kind of thing, you will actually see different parts of the brain lighting up, which is a much more rewarding way of kind of getting at the questions we've been asking forever about which bit of the brain does which work. Now, part of the problem there is that brains are really complicated and they are evolved, which means they're messy. So, it's rare that you can say, oh, there's the exact bit of the brain that does this. But nonetheless, you can see regions of the brain that are using more energy under different circumstances. And it's a much more rewarding way of addressing those questions than what we used to have to do, which was essentially to stick an electrode into one particular part of the brain, hope you hit a neuron.
Oh no.
What's that?
Oh no.
Oh, yes.
But I suppose one can image in infrared or temperature at least over the surface. I mean, you can't do deep down, I suppose, but I can imagine that it'd be interesting to image the temperature of the surface of the brain in real time.
Well, EEG would do it.
You can look at things like oxygen usage in the brain, which is
okay, it's correlated. Yeah, it's correlated. So.
Well, the problem with temperature is that your blood system is cooling the brain constantly and carrying the heat away. You don't lose the bulk of your resting metabolism is up here, but you're losing the heat from all over your body because the blood is carrying it around.
Uh-huh.
Yeah, I just found the statistic using trusty internet that the human brain is responsible for 20% of the body's energy budget. Abby, I think the human brain is something like 5% of our material mass, but it's 20% of the energy.
It's a real energy hog. Interestingly, speaking of that, and speaking of sort of favoring choice, for lack of a better term, not active conscious choice, but chickadees. You're probably familiar with chickadees, little birds, about this big with the cute little black caps and everything. It turns out that they actually lose part of their brain every winter. And then it grows back in the spring. So, I guess when they need to be doing more things having to do with nest building and otherwise being active in their environments, their brains actually grow in the spring, and then in the winter, when it's cold and there's not as much food and they need to save energy and the like, their brains, some of those neurons go away again.
I wonder if this something similar happens to hibernating, other hibernating animals like bears or frogs.
Yeah, I'm not sure if they use brain mass or if everything just gets turned way down, or rather I can say I know everything gets turned way down. I'm not sure if they lose brain mass during that time or not. I mean,
I feel
certainly.
like it happens to me all the time. So.
Especially in the winter, Ivan. Yeah.
Yeah, I was thinking of that 20% budget. When we go to sleep, our large muscles, they just sort of collapse and they're not doing anything. But the brain is still active, as we pointed out. So this is part of that budget. The brain never shuts off. Yes, it reduces the amount of activity, but even at the low level of activity, it's still bustling, it's still churning, it's doing all sorts of crazy things, and we have no idea what it's doing. It's just active. So it's sort of like an engine that's normally running at 8,000 RPM, and it slows down to 4,000. It's still going really fast. It's just
it does shut off though, Joanne, but only once.
And we try to avoid that. And the other thing they've been doing with electroencephalograph, they've got full skull caps.
Yeah.
With 30, 40, 50 different things that they're monitoring the brain all at the same time. And again, it's much more comfortable to sleep in an MRI. And they're looking at the brain and seeing this incredibly active device and going, oh, we didn't know that. It's just incredible. And then the third thing is when you have a stroke and it physically destroys part of your brain, that you can recover in two different mechanisms. First off, the brain is plastic, so other portions of the brain can pick up those activities and ultimately do the job just as well. And you can, in fact, create new cells in that area, picking up that function. And in many cases, it comes back as completely the same amount of skill and ability as you had in the past. So the idea that the brain is just going away over time isn't true at all.
Well, there's
I'm not sure, by the way, that the 40 electrodes is less comfortable than having an MRI of your head. I've never done the 40 electrodes, but I have had an MRI of my head, and it is loud. I don't know how you could sleep.
Bang, bang, bang.
Well, one of the things that I know about physiology is that during the teen years, preteen and early teen years, there's a really significant pruning of neurons that happens in the human brain.
At puberty.
The question that really interests me, I mean, a future Nobel, let's see, I can remember a nursery rhyme from when I was 3 or 4 years old, and it's in there somewhere, but we have no idea. I mean, it's probably not localized, in which case, if you just cut out a little bit of the brain, that would go away, that memory would go away. It's probably more distributed, some holistic thing.
Like a hologram.
I mean, this is something am I right? I mean, we just don't understand how memory is stored at the physical, chemical level. I mean, it's complicated, right? But it's something we've got to find out in the 21st century about that,
I don't want to say that we know everything about. Sorry, Abby, go ahead.
I was just saying, there's still a lot that we don't know. And, unfortunately, we kind of like the idea that, you can, if you look at the digestive system, you can say, oh, there's the stomach. And you find out what the stomach does, and it has a bunch of specific functions. Or, there's the spleen. But when it comes to the brain, it's like, it's in different lobes, and there are some various different bodies within it. And some of them do have specific functions. Mm-hmm. But at the same time, if you want to say, so, where's that nursery rhyme stored? That's not something that's likely to be like in one particular file drawer in one particular place. People used to wonder that even about vision.
Right.
Is there one particular cell in your visual field that stored your grandmother's face? This was known as the grandmother cell. And the answer is, probably not. That's certainly not the way vision works. And so not the way other stuff works either. That said, there will be general regions of the brain that will deal with language, for instance.
I remember a study about that, the grandmother cell, that said that it was an interesting hypothesis, but if it turned out to be factual that you needed a dedicated neuron to recognize each distinct shape that you can, including faces, that you would need so much brain real estate just to process faces that it doesn't make sense from a physiological standpoint. You cannot have dedicated cells to each face. It doesn't fit.
I want to say something about neural networks, that there are lots of things about the brain that we don't understand yet. But the general mechanism of the neocortex, I think we have some relatively mature theories about how that works. And that's some of the things which have been mimicked in software.
Mhm.
The neocortex is very general in its architecture. So what the neocortex does, or part of the neocortex does, depends on what it's connected to. And that's where a lot of the plasticity comes in. And so we actually have pretty good models of how the neocortex works. There's a wonderful book by Jeff Hawkins called On Intelligence that explains, puts forward a very compelling model of how it works. And it's the same, and it's been replicated in software. So we know that it can do some of the things, like it can learn just from experience. There are also lots of other details we don't know about how the brain works. But I don't want to say that, you know, it's a great mystery. We have no idea. We actually know quite a lot about potential mechanisms for it.
Oh yeah, we're getting a better idea of it all the time, but there's still, let's just say there's a lot of work to do still.
Do you think the analogy with the hologram is a reasonable analogy? That you have a hologram and it's got the image, but if you cut it in half, you still have the whole image, but less well defined. So the information is spread out over the whole. So if you cut out sort of half your part of the brain has memory, you'd still have some memories, but it'd be more fuzzy. You wouldn't lose things. I mean, it's just an analogy, I suppose. But yeah, but eventually, if one actually is able to, you can imagine down the road being able to read out people's memories. Okay, somehow, you know.
Yeah, I've read back in, I don't know, 10 years or so ago, I think this notion of the holographic brain was fairly common. I don't know what's,
But it sort of went away.
yeah, I don't know how much that's been developed, but it does play on this idea that you cannot have a dedicated neuron to a face.
Yeah.
And that memory, you don't have the nursery rhyme neuron or the 4 nursery rhyme neurons, that there is some aspect in which memories are processed and stored in a network manner, kind of what Ivan was talking about with neural networks, and that the networking, the interconnectedness is really important. Now, whether that translates directly to a hologram or not, I haven't read much.
There's been
recently.
work done on PTSD. Again, when an episode occurs, you can physically see it in an MRI. So when you get the fMRI going, and it has been physically done, that they've opened up the skull, found that particular area, and put an electrical probe in and zapped it. And the PTSD symptoms really changed and were lessened significantly because that particular portion of the brain was just destroyed. And this is one of those things where, is this just the nexus? Is this just the starting point for a large association
yeah.
going on? And we've destroyed the original starting point for this whole thing? Or is this what trauma looks like in the brain? Whereas all of the memories are distributed, that a trauma occurs right there.
Yeah.
And it, so again, huge areas of, we don't know.
Yeah.
So in neocortex, it's arranged in a hierarchy typically. And each level in the hierarchy is creating an abstraction of the layer below, like it's making predictions about what it will see next. So in vision, the lowest layer might correspond to something like pixels. And then the next layer would be edges. And then you'll have vertices, and then you'll have color and so on. And so if you imagine, you know, you're looking straight ahead and a rabbit climbs into the scene and walks across, you know, your field of vision, at the lowest level, the pixels are changing, right? There's all these pixels changing as the grass is blowing in the wind and the rabbit is moving across. But then the different layers, at some layer higher up, there's an abstraction for a rabbit.
Mhm.
When
Mhm.
a rabbit walks into the scene, that neuron turns on and says, there's a rabbit in this scene.
So I have to give us a time check here. We're at 3:30, and
Wow.
that's our 90 minutes. I would
4:30.
like to close out with the idea that all of this points to the fact that our consciousness, our intelligence, our behavior is purely, solely, and exclusively, I don't know how many more synonyms I can use, a result of what the brain does. The brain still has a lot of mystery to it. We don't know how it stores memory, how it processes information completely, but you are your brain.
I'm here.
And this is a good,
I'm in here somewhere.
consistent with humanism, the idea that monism versus dualism. We are just biological, incredibly beautiful, complicated,
We're cute, right?
competent, artistic, wonderful machines. And it's good to know, it's good to be on a planet where I get to meet and interact with other beautiful machines such as yourselves. So thank you.
I completely agree. I don't think there are supernatural things going on, but I do think that a disembodied brain would not be recognizably human. I think that part of what makes us think and feel and all that is the interaction between our brains and the rest of our bodies.
Right,
I
sure.
think that's extremely important, and simply say that we live only in our brains is not to understand how it works.
Yeah, I actually agree with you, John. I apologize for oversimplifying.
So a wonderful topic, perhaps for next time.
Right.
Does this mean that we could actually take your brain, put it in a jar, keep it alive, and put it in a new body at some future time, and you would exist? Or would you be a different person entirely?
Yeah, if I had thicker bones accustomed to gymnastics, I might be a different person. So anyway, let's pick this up again next time. Thank you all so much. We had a really
Wonderful to see you guys.
wonderful conversation. And oh, by the way, the next time will be on Halloween. I hope you can make it. It'll be 2 weeks from now on Halloween Saturday in the afternoon. So
I'm looking forward to seeing your costumes.
Oh, good idea. Good idea. And we'll try to come up with a couple scary topics.
Yeah.
Yes, ghosts.